Hello everybody, welcome back to another video, and today we're going to be going over the monotone convergence theorem. So this will help us prove if a sequence is convergent or not. So the first step is to determine monotonicity. Monotonicity is basically just saying is it's always decreasing or it's always increasing. So if we look at the monotonicity of this sequence right here, we have to relate the n plus 1th term of the sequence to the nth term of the sequence, and it has to be either an increasing function or a decreasing function. And it has to always be like this. So this has to be true for all n. So as you can see here, this will be the case because if you plug in a number like 2 into here, you'll get 0.5. And if you plug in a 3, which is the next term, you get 0.6 repeating. So that is obviously true. And then if you keep going down infinitely, it's always going to be the case. And you can also take a limit if you want to really figure it out. But it is always going to be always decreasing. It's always going to be increasing function, sorry. So now we need to know that it is bounded. And this one is bounded because if we look over here, we know that 1 over n always has to be greater than 0 because remember, n is just our term in the sequence, so it can't be 0. It has to be like 1, 2, 3. Can't be a decimal. So 1 over n has to be greater than 0. So 1 minus a number greater than 0, like 0.5, is always going to be less than 1. So this means that a of n is less than 1 for all n. So what this means is that we know that the sequence cannot be greater than 1. So what this means is that it is bounded by 1. So we had just checked 2 boxes, and now we know that the sequence converges. Converges by MCT. Let's move on to the next example. We have 1 over n squared. We want to prove that this sequence converges using the monotone convergence theorem. So if we check the monotonicity, we have 1 over n plus 1 squared. And we're going to relate this to 1 over n squared. So if we look at it, since the number in the denominator is going to be bigger on the next term, that means that the number is actually going to be smaller. So 1 over n squared is going to be bigger, a bigger number. So this means that is a decreasing function, and it's always decreasing. So now we got to check the boundedness. Of course, because we have a fraction bar, and n always has to be positive, and we also have a square too. So even if if we could have a negative n, it has to be greater than 0. So it's bounded below by 0, and it's decreasing. So that means that it does converge by MCT. So now let's move on to, I'd say, the most elaborate example, but still relatively a simple example. So sequence of partial sums, we're going to check monotonicity. And since it's a sum, each term is adding, and we're adding positive terms, meaning that it is an increasing function. And we know that if we were to take an infinite sum right here of 1 over k squared, this will be less than infinity, or it will converge to a number. And the reason we know this is because it's a convergent p series. So if you just remember your p series, you remember that 1 over k squared, the infinite sum, it actually converges to pi squared over 6. The exact reasoning behind that isn't in the scope of the video, but it's a cool fun fact to know. So this means that it's increasing and it's bounded. And you can also just look as well at when you sum numbers like this, where you have 1 over 1 squared, which is 1, plus 1 over 2 squared, which is 1/4, so 0.25, plus, obviously you could keep going, more and more and more, but you know the numbers aren't going to get any bigger. It's not going to infinity ever, really. So that's why it goes to pi squared over 6. Obviously, the exact number is difficult to compute, but you can just tell that it will not go to infinity just by looking at it. Anyway, I'll see y'all later, and goodbye.